My name is Declan Bainbridge, and this is my physics student-directed study. My focus question is, what is quantum entanglement, and can it be used for faster-than-light communication? In this video, I will attempt to explain what quantum entanglement is, and if it can be used for faster-than-light communication. After that, I'll look at what the future may hold for quantum entanglement based on a recent paper by Google. But first off, what is spin? Spin is something that I will be talking about a lot, so I think it is helpful to know a bit about it. Spin is defined as the intrinsic angular momentum of an elementary particle. What does that mean in simple terms? Well, imagine a ball that is spinning, except it's not a ball and it's not spinning. That may seem ridiculous, but unfortunately that's kind of just how quantum mechanics is. Spin is a fundamental property that particles have, similar to mass or momentum or charge. For the purposes of this video, I won't go too in-depth. However, I think a basic understanding will be helpful when examining quantum entanglement. Spin can be thought of as an arrow that can point in any direction, except when we measure it, it instantaneously decides whether it should be all up or all down along the direction that we measured. Here is an example of an electron with an up spin. If we took the same electron and measured the spin horizontally, then we would find that spin is either left or right. Experimentally, we know that when a measurement is taken, the electron has a 50-50 chance of collapsing into an up or a down spin state. It is easy to make the assumption that the electron already has a defined state, and by measuring it, we are just figuring out what is there. In fact, if you make that assumption, you would be among many great scientists, including Einstein himself. Prior to researching for this video, that was my understanding as well. That way of thinking is called hidden variable theory, HVT, and it was a hot topic in the early 20th century. Hidden variable theory has been proved false, which I will touch on later in the video. For now, I will just assume that there are no hidden variables. If there are no hidden variables, in other words, the electron does not know the direction of its spin, then what is really happening? The phenomenon at work is called quantum superposition. Quantum superposition is one of the many behaviors of quantum particles that unfortunately just doesn't make sense in any other context. Quantum superposition means that a quantum system, an electron in this case, is actually in multiple states at the same time. That is extremely important to understand. Our electron is not secretly spinning in some direction that only it knows. The electron is spinning both up and down simultaneously. By measuring the spin, it forces the electron into one of the states. That introduces another mysterious quantum behavior, the observer effect. That is a whole can of worms that will be saved for another project, but for our purposes, you only need to understand that when a particle that is in a superposition is measured, the superposition collapses and the particle will pick one of the normal states, in this case, spin up or spin down. I would also like to note that superposition is not just a clever mathematical trick to make the equations of quantum physics make sense, it is actually a testable idea that has been proven, as far as we understand. The behavior that I just described as the electron picking either spin up or spin down is known as wave function collapse. The state of the electron when it is in some kind of superposition is known as a wave function. The wave function of a particle is how physicists mathematically describe all of the things that a particle could be doing in terms of how likely those things are. This wave function is the heart of particle-wave duality, which says that particles are waves until they are measured, in which case they collapse back into particles. Now, what is quantum entanglement? Well, quantum entanglement is a topic that is frequently oversimplified. That is not without good reason, however. The moment you begin to look too closely at the phenomenon, it becomes a horrible mess of linear algebra and complex numbers and vector spaces and other crazy stuff. My goal for this project is to provide an intermediate look at the topic, one that goes beyond the simple explanations but remains understandable for the average curious mind. I will introduce the concept with the classic example. Quantum entanglement is, in its most simple form, a phenomenon whereby two particles, say electrons, are related in such a way that measuring one instantaneously affects the state of the other, regardless of the distance between the two particles. First, imagine two regular electrons separated by a great distance being measured. Let's say that one of the electrons belongs to Alice and the other belongs to Bob. The spin of each particle has a 50-50 chance of being up or down, and Alice and Bob's measurements have no effect on each other. However, if the electrons are entangled, that means that when Alice measures the spin of one particle, the result of measuring the other particle must be opposite. That happens regardless of where the electrons are or when the measurements take place. In fact, not only is the measurement of the second particle certain, but the moment that either particle is measured, the wave function of the other instantaneously collapses. The spin of one particle is instantly defined when the spin of the other is measured. It is as if there is some kind of connection between the particles that transcends time and space. That view of quantum entanglement is not exactly wrong, but it is far from complete. In reality, the results of the measurement are more probabilistic and aren't necessarily guaranteed. In the example above, the particles are considered maximally entangled. That means that a measurement of one guarantees a definite measurement of the other. For later reference, two maximally entangled particles like this are called an EPR pair. It doesn't have to be the case that the two are exactly opposite, however. Particles can be less entangled as well. If the particles are not entangled at all, Alice can only predict Bob's measurement with 50% accuracy, a blind guess. If the particles are entangled to some degree, Alice can actually predict with better than 50-50 odds, but not necessarily 100%. There's still uncertainty. Furthermore, spin is not the only property that can be entangled. Any quantum property can be entangled, such as charge or momentum or the polarization of photons, and more than one can be entangled simultaneously. Adding even more to the complexity, the states of more than two particles can be entangled. Devices like quantum computers rely on many particles to be entangled simultaneously. I will come back to that at the end of the video. Quantum entanglement is a completely bizarre idea that has puzzled many of the greatest physicists, including Einstein himself. In fact, Einstein refused to believe it. Albert Einstein, Boris Podolsky, and Nathan Rosen published a paper in 1935 which became known as the EPR paper, asserting that quantum mechanics was incomplete and describing the necessary existence of a hidden variable. A common misconception about quantum entanglement that I myself held before researching this is that when the electrons become entangled, they secretly decide which one will fall into which state, and that information is hidden until it's measured. It is easy to fall into that idea because it is the only way that quantum entanglement can really make sense to us in the classical world. Surely there must be some kind of predetermined decision that allows the electrons to have exactly opposite spin. Except that there's not, and it is actually proven. In 1964, a physicist named John S. Bell came up with two inequalities based on statistical analysis that, bizarrely, could prove or deny the existence of hidden variables. Think about how strange that is. A mathematical expression can prove or disprove the existence of something that otherwise cannot be observed or interacted with. The inequalities, if they held true, prove the existence of hidden variables. If violated, hidden variables would be impossible and demonstrably non-existent. Suppose that there are two spin detectors. The detectors can be oriented in any way relative to each other, and let the directions of said detectors be denoted by vectors a and b. Now imagine a function, p of a and b, where p represents the prediction of the correlation between the two measurements. The correlation is the opposite of the dot product of the vectors. In simpler terms, if the detectors are perfectly perpendicular, they are not correlated at all. If they are anything other than perpendicular, there is a correlation between the two. Detectors have a chance of measuring similar results. If you then set up a third detector with direction C, you have a choice between detector B and C. Bell's inequalities state that the difference in correlation between the detector using A and B versus using A and C must satisfy the following equality. By setting A and B to be perpendicular with C right in between them, P of AC and P of BC are both equal to negative root 2 over 2. Plugging that into the equality from before, you can see that the equality is violated. Just like that, HVT has been theoretically disproved. In practice, however, it took until 1972 to come up with an experiment that could test what became known as Bell's inequalities. John Clauser was the first person to come up with such an experiment, and it showed that Bell's inequalities could be violated. His experiment contained some flaws, so further experiments by Elaine Aspect and Anton Zellinger, among others, were conducted which improved upon the original. After Anton Zellinger's experiments, virtually all flaws in the experiment were worked out beyond a reasonable doubt, and Bell's inequalities were violated with almost complete certainty. Those three physicists won the 2022 Nobel Prize in Physics for their work in disproving hidden variable theory and supporting quantum mechanics as we currently understand it. So, armed with an understanding of quantum entanglement, it is time to look at its use cases. At first glance, it seems like the information that quantum entanglement provides can be used to send some kind of signal faster than light. Going back to the example from before, if Alice measures her particle to be spin down, then somehow has information been transmitted to Bob instantaneously? The answer is no. However, the why is a bit more complicated. Long story short, Einstein's relativity says that no information can travel faster than the speed of light. If it could, it would violate causality, aka travel backwards in time. So knowing that, the answer to any question about so-called superliminal signals is always a no. But I still think it is important to look at why the answer is a no, because there are so many subtle ways that it seems like it can happen. First, let's consider the most simple example. Alice and Bob start on Earth and entangle their electrons, then fly to opposite sides of the universe. Before they depart, Bob asks Alice to measure her particle when she arrives safely. Alice does just that, and upon arrival sees that her particle is spin up. That means that Bob's particle is spin down. But was information transmitted to Bob? No. Even though Bob's particle was affected, there's no way for him to tell unless he himself measures his own particle. But then what? As far as he can tell, the particle is just spin down. That doesn't really convey any information. He doesn't know that Alice measured her particle. If he made a slight change to this setup, it could work. If beforehand they decided that Alice would measure spin up if she arrived safely and spin down if otherwise, then by measuring his own particle, he would know Alice's message. If he measures spin down, then Alice arrives safely and vice versa. However, you fundamentally cannot force a particle into a specific state such as spin down. If you do, it would break the entanglement. But what about some more crafty ideas? Let's say that Alice and Bob agreed that Bob would wait 5 minutes upon arrival before making his measurement. Alice, upon arrival, would keep measuring her electron over and over until she got her desired measurement. Then, after 5 minutes, Bob measures his, and he knows that he got the opposite of what Alice got. That doesn't work, because the moment Alice makes her first measurement and collapses her electron's wave function, the entanglement is broken. Entanglement is like a one-time deal, and you can't set it up over large distances. Once her particle has been measured once, that's it. Now imagine that instead of one pair of entangled electrons, they each bring a whole bundle of entangled pairs of particles arranged in a line. Alice then begins measuring them one at a time until she gets the desired result, at which point she stops. Bob then measures his one at a time until he notices that one switches. At that point, surely he knows that Alice stopped and he got the message, right? No. Since the very first particle could be the right state, Bob can never know if the following states are right or wrong. For example, if Bob measures 3 up then 1 down, he may think that the fourth particle must be the one that Alice intended to communicate. However, what if the first particle was the one she intended to communicate? In that case, the 3 subsequent measurements were purely random because Alice didn't even measure them. Another idea is that Alice and Bob agree beforehand that a horizontal measurement means a 0 and a vertical measurement means a 1. Then, when Alice intends to send a 1, she measures the left or right spin of her particle. By definition, Bob's particle has now collapsed into the opposite of whatever Alice's state was. So all that Bob needs to do is measure the spin of his particle, right? Well, no. There are a few situations that can play out here. First off, assuming that Bob is measuring his particle after Alice sent her message, then he needs to choose which direction to measure along. Remember that by definition, to measure spin, you need to pick a direction first. So, Bob has no way of knowing if he's measuring the correct direction, or even if a message has been sent at all. There is no way to detect which way Alice measured her particle without some extra information that Bob cannot have. Again, no dice. What happens if we move on from just simple measurements of the spins and get even more crafty? We will go back to the example of them each having a bunch of particles, but this time all of the particles are entangled in one big lump. When Alice measures her particles, it collapses the wave function of all of the particles. That is a fact. So, if somehow you could measure whether a wave function has collapsed or not, you could tell when Alice had made her measurement. You can actually do that very simply with the classic double slit experiment. Bob can start shooting his particles through the double slit and watch to see whether or not an interference pattern forms. If it does, it means that the particles that are passing through are acting as waves, and therefore Alice has not collapsed her particles. If all of a sudden they no longer form an interference pattern, then Alice must have measured her particles. This must be a solution, right? So close, but no. The reason that it's a no is unfortunately just because. If it were a solution, that would mean that causality could be violated, and that just can't happen. For reasons that I frankly don't understand, when one of two entangled particles is passing through a double slit, it acts only as a particle, not a wave. To get an interference pattern with an entangled particle, both entangled particles have to be passing through the double slit machine. As I have described, there is no way that quantum entanglement can be used to communicate faster than light and thus violate causality. The example of Alice and Bob taking one particle in opposite directions is akin to them each taking one shoe of a pair. If Alice opens her box and finds a left shoe, Bob has a right one. Despite knowing that instantly, no information has been transferred. When considering questions of logic with quantum entanglement, I find it easiest to think of it more in terms of symmetry. If one particle is created with momentum going up, then by conservation of momentum, another has to be created with momentum going down. Those two particles are then entangled in the sense that their momenta must cancel out. If we can't use quantum entanglement for FTL communication, can it be harnessed for anything useful? Absolutely. Some notable examples include quantum cryptography, quantum computing, and some studies even say that photosynthesis in plants may rely on it. I won't go into details about those other ones because this project can only cover so much. However, in doing a project about quantum entanglement, I would be remiss if I did not talk about Google's recent paper that made quite a few headlines and caused some controversy. First, I'll start with wormholes, also known as Einstein-Rosen bridges, named after the two scientists who pioneered the idea. It may seem unrelated, but I'll get to that. A wormhole is a theoretical structure that may be formed when two black holes rip holes into the fabric of space-time, and those holes happen to overlap. In that scenario, a theoretical craft that doesn't obey physics could fly into one black hole and come out of the other, thus finding a sort of shortcut through space-time. In reality, nothing could travel through a wormhole because the wormhole would instantly collapse. That is, unless you send a huge pulse of negative energy along the wormhole while some particle or craft is traveling. In 2013, a radical paper was published by Juan Malsadena and Leonard Susskind that proposed a conjecture that says that an Einstein-Rosen bridge, a wormhole, is mathematically congruent to an EPR pair. In other words, a pair of maximally entangled particles, such as the electrons from before. The theory came to be known in shorthand as ER equals EPR. Conversely, the theory states that entangled particles effectively create a super tiny wormhole between them that allows them to influence each other instantaneously, since from their perspective they are right next to each other. Without going into too many details, the experiment recently conducted on one of Google's quantum supercomputers used two sets of 7 entangled particles to sort of represent the two sides of a wormhole. I say represent because not only is the wormhole a one-dimensional line in a technically incorrect spacetime, but it is also literally using as few particles as possible to just sort of simulate the behavior of a theoretical wormhole. They call it a holographic wormhole because technically it is like a projection of higher dimensions onto lower dimensions, but that itself relies on some stuff that is technically a tiny bit wrong, so it's just an approximation. Anyways, by swapping one of the 7 particles with the particle to be sent, it collapses the wave function of the 7 on one side. A magnetic pulse rotates the particles on one side and kind of sends the information on one side to the other side. This magnetic pulse is congruent to the shock wave of negative energy that would be needed to traverse a real wormhole. What the researchers found is that the particles on the other side of the wormhole still contain the information from the first side, and the information was actually sent through. This experiment was extremely complicated and far beyond the scope of this project, but it has interesting implications for the possibility of a unifying theory of quantum mechanics and gravity, which has eluded physicists since the early 20th century. Right now, the theories are in their infant stage and still full of holes. The experiment received a lot of backlash as a result, but I don't think that is entirely warranted. Classical mechanics worked well for hundreds of years without accounting for relativity, and I think that this is similar. Right now, it's an approximation of a simplification, but it's a start. Throughout this project, I've examined what quantum entanglement is, if it can be used for FTL communication, it can't, and some interesting developments regarding quantum entanglement in the future. I hope that this video has taught you something interesting, and I hope that you enjoyed. Thanks for watching.